So this is the material we're talking about last time. So we're talking about fluid statics, fluid pressures in static fluids. You'll remember that last time we did a derivation basically for this expression here, which is kind of oxymoronic. We made the point that we're looking at an accelerating fluid even though the fluid is static, but that means that the fluid in the container is not circulating. So it's like gas in a gas tank as you drive down the road, or fuel in the wings of a plane as you take off, for instance, or the beverage in your hand, which you're not allowed to have in your hand as you take off, for instance, or in your car, God forbid, as you drive down the street. We came up with a number of expressions. This one we didn't derive, but let's take this on trust. This basically says that if you take a fluid at a particular point, the pressure acting vertically and horizontally at that point is the same if it's static. And so that's an important thing for us to realize. We didn't derive it, but let's take that on trust. We also did this evaluation for fluids that are accelerating. So if the fluid is moving in the elevator at some velocity, then there's this extra term. If these terms happen all to be zero, which is really the case we're dealing with now, we'll talk about accelerations in due course, then the only term, the principal equation that's of interest to us is this one, is how pressures change as you go vertically. We've chosen this x, y, z coordinate system, which is right-handed. Whoops. And the one important thing to remember is that our z direction is positive upwards. Gravity is in the negative z direction, opposite that. Z is always in the opposite direction to gravity. And if we do that, then if you look at this expression, then we get a couple of relevant expressions. This is the important one. This tells us how pressures change as we go up and down. It's proportional to the unit weight. And the other important one is, well, it's equally important, is that the pressures in the horizontal plane are zero. So if you go from A to B and you don't change elevation, then the pressure at those two locations are the same. And actually we've kind of used that already. You might not well, we did say it when we did it, but if you remember when we talked about a capillary tube, what we did to analyze that was we basically took this and we cut it off at the base, and we said that the pressure acting here is atmospheric. And the reason for that is that, whoops, the reason for that is that the pressure here is atmospheric, and I think we did mention it. And if we go into here to this point right here, since it's connected and we can get there in the same fluid, then the pressure here also has to be atmospheric as well. So it means we can just cut the bottom off it and lift it up, and the analysis that we did was by just doing the force balance for that. So we've used this already, even though we haven't acknowledged it at the time, because we hadn't looked at it yet. If we take this expression and we integrate it for a fluid that doesn't change density with pressure very much, like a liquid, most liquids, all liquids really, then we can get the pressure at a point as being the pressure at some other point, plus the change in elevation from those. Typically you'll use this expression, and the only other thing that you need to remember in doing this is that if you use h as the elevation change, then h is positive downwards. If you go from point 0 to point P1, say, if this is P1 and this is P0, then you're going down in this particular case, so h is positive. If you're doing the opposite, if you're going to a point up here, P1, then h has to be negative. Minus VE is my shorthand. I remember going through classes for the whole class, like, what the hell does minus VE mean? It's negative. It's my shorthand for negative. And you see that down here as well, right? We haven't talked about this yet, but we'll talk about manometer rules today. So that's kind of where we got to last time. So it's right here. So what I wanted to do today was to talk about cases where the fluid, or the fluid, is no longer incompressible, but is compressible. And so one concrete way to think about this, I was going to do an example when we're talking about vapor pressures. And that example was going to be looking at, for instance, Mount Everest. So, of course, Mount Everest doesn't go down to sea level, but let's pretend it does. We all think that Mount Everest is the tallest mountain on the planet, but is it? What's taller? Sorry? Yeah, that's right. Hawaiian Islands. Because if you measure it from the seabed. And so, but Everest is something like 29,000 feet, right? So it's about 10,000 meters. And so what you could do is, if you want to what I was going to do is I was going to calculate what the pressure was at the top of Everest, so that we could calculate what the boiling point of water would be if you heat it up. And you know that if you reduce the pressure, then the temperature you have to raise water to is no longer 100 degrees centigrade, it's perhaps 70 or 60 or 50, depending on how high you are. And so to do that calculation, of course, we could use this, if we assume it's incompressible, then this is P0, this is P1, this is H, and it's about equal to 29,000 feet. I guess 33,000 feet would be 10,000 meters, but that's not split hairs, so to speak. To see how my arithmetic is today. It hasn't been doing very well so far, right? So the lightning calculation, right? 600 miles an hour is 10 miles a minute, which is a mile every 6 seconds. I'm not sure we said that last time, but count 6 seconds and it's a mile away. Tsunamis, we said, travel at about 100 meters a second instead of 330, which is the speed of sound. So they travel at a third of the speed of sound. So it would take 18 seconds for a tsunami to get to you, right, from being a mile away, which is interesting. That's very fast still. Anyway, we digress. So we can calculate... Sorry? Yeah, go ahead. Can you shout? What about that? 10 to the fourth. So 1,000 meters would be 10 to the third, and 10,000 is 10 to the fourth. Yeah, so it is. Yeah, fine. Yeah, thank you. It's good to check on me. Because, so anyway, so the pressure at... by the way, if you want to ask a question, some of you say professors, just say question, and shout it, and then I'll hopefully respond.
Question.
Yeah.
When you say it was taller than Mount Everest?
Say it again?
Said something was taller than Mount Everest.
Yeah, the Hawaiian Islands, from the seabed. If you look at the route of Mauna Loa or Mauna Kea, from the seabed up to the peak of the volcano, then it's certainly taller than 10,000 meters. I don't know how much more. So it just depends on your reference frame. I mean, Mount Everest is certainly 29,000 feet, but it's landlocked, and certainly in the foothills, which kind of flatten out, I imagine you're probably at 10,000 feet or 3,000 meters by the time you're there already. So yeah, the Hawaiian Islands. It just depends. It's a party trick. You can amaze your friends in the bar with that little piece of information. If you can remember it. All right, so let's get on with this. Am I recording this? I guess I am recording this. So unit weight times h. What do we say about h? Well, h in going from this point to this point is up. So this is down. So this is negative rather. And so this is what? The pressure at point 1 is going to be equal to atmospheric pressure. What's atmospheric pressure? 100 kilopascals, right? Or 10 to the 5 newtons per meter squared. So this is 10 to the 5 pascals, or let's use newtons per meter squared. And it's minus the unit weight of air. This is the thing we did wrong. I did wrong the other day in calculating the speed of sound in air. I used the unit weight of water, which is 1,000 kilograms a cubic meter. The density of air is about 1 kilogram per cubic meter. So it's about 1,000th of the density and 1,000th of the unit weight. So if the unit weight of water is equal to, say, 10 kilonewtons, so 10 to the 4 newtons per meter cubed, which is what water is. Then the density of air, if it's a thousandth of that, is about equal, it's 1.2 or something, kilograms per cubic meter. So this would be 10 to the 1 newtons per meter cubed. And so if we put this in here, this is 10 to the 1 newtons per meters cubed multiplied by the height, which is 10 to the 4 meters. Then you end up with, hence my reason for not doing this example, is 0. The pressure is 0. We know it's not 0. It's 0 pressure in a vacuum. And if you go into space, the reason people wear spacesuits is because you have to deal with the vacuum. If your spacesuit gets punctured, then basically you vaporize, right? Because we're just moisture, we're water primarily. And so this would suggest that liquid water couldn't exist on the top of Mount Everest. I mean, we know you can. People drink water, they take snow, they boil it, it boils at a lower temperature, but nonetheless you drink it. So we can't use this. So presumably the pressure isn't quite as low as this predicts. And the reason that this is a bad prediction is that the density of the fluid, what we're basically assuming is we have a can of air which sits here, and that can has some weight in it. We could calculate what the pressure is that is applied here, and due to holding up this weight of fluid, we're just calculating what the pressure is at this point, which is we're calling P1, and that's what this number here is. And so clearly this isn't the true pressure. It's not a vacuum on the top of Everest. Otherwise you'd need more than oxygen to be able to get up there. You use oxygen to supplement what you're doing, not just because there's no air at all, just because the air is thin. So what's happening? It's obvious, right? What's happening is that the density of air is changing as you go up in elevation because the pressure is changing. It's getting less dense. And so what we can do is we can deal with the case where that's the case. So let's go ahead and look at how to do that. Okay? So, all right. So where are we? It's a short week this week, right? So it's fluid statics still. And so what we want to do today is, this is compressible gas, a compressible fluid. All right, so, well, let's draw our picture that says exactly what's going on. So the picture is this. If we look at the change in pressure that occurs with elevation, not very straight, but these are supposed to be straight lines. Positive Z is upwards. If this was, for instance, water below here, we know that this is what we talked about last time. The whole reason for this expression, change in pressure with elevation is equal to minus unit weight, says something about the fact that this is a change in elevation, this is an incremental change in pressure, and if we look at that in terms of what this expression means, just by similar triangles, right? We did this last time. This is equal to 1, which is dz. These two correlate. This is equal to dp, so this is unit weight, right? And so, for instance, we said last time, if you go deeper in water, it gets a bit more dense because it has more pressure. It's slightly compressible, and so it has more pressure acting on it. So it would fit in a smaller volume, and so therefore, by definition, it's more dense. So this expression here is true at every point, and it's true in the simple integration we did if this is linear, just by the analysis we did last time. But we think, for instance, that if it gets perhaps more dense with depth, this is equal to gravity times the density. So if the density increases, we'd expect that this length would get longer. And so at some depth, we'd expect that this, if we had some finite compressibility, then this curve, if I can do it, should curve away in this direction, right? In this direction, right? Means it's in other words, if we look down here, to exaggerate it, this one and this unit weight, this now is larger than this length. So we know it has to be that case. If it gets denser as you go deeper, that's the case. So this is water. If you look at air, I guess I could write N2, right, which is basically what it is. Then this is still true as we go up here, and we drew this last time, still the same case, but now this height 1 and the unit weight we know is a factor of 1,000 less. So this curve here would be different in two ways. One, it would be almost parallel to this axis on this scale, right? Because this magnitude of air versus water would be 1,000th of this length, right? It'd be related by 1,000. But also, because air is compressible, we'd have to worry about the fact that this really should curve. And I haven't drawn it very well, but as you go up, you could imagine that this would get steeper and steeper and steeper. And we can show that that should be the case based on the rationale of this, right? We said that as you go deeper, it gets more dense, and therefore this should be larger. So by corollary, as you go higher, this should get much less dense because it's compressible. And so this length here, unit weight, should get smaller and smaller. And so in other words, it would curve towards the vertical. So what we can do is we can calculate, we can do exactly the same as we did before in terms of integrating this expression between two arbitrary locations. Doesn't matter where those locations are. Let's call them Z1 and Z2. And at those locations, pressures 1 and pressures 2 exist, right? So this is Z2 where there's pressure 2 exists. And so what do we have? Well, we have this expression that change in pressure with elevation is equal to minus unit weight, which is equal to minus density times gravity. We also know that we have the ideal gas law, where pressure is equal to density times the gas constant for that gas times temperature. And so we could certainly rewrite that in terms of density, as density is equal to the particular pressure at that location divided by RT. So just rearranging that. We could certainly put it in here. And so we'd have something that says the change in pressure with elevation, this is pressure, not density, is equal to minus gravity times rho, which is pressure times RT. And we can certainly rearrange this expression so that we have Z on one side and everything involving pressure on the other side. And so in other words, we'll skip this over here, the pressure. And so we'll end up with change in pressure 1 over pressure. And we'll migrate everything to the other side, which is minus the rest of this term, G over RT, which is the remainder of this, right? And this term here, times dz. And so this is true every single location along here, but it's not, the problem is that the density isn't constant, clearly. This is the density term. And so it changes as a function of pressure. And so what we can do now is we can integrate this, and we'll integrate it between the pressure that we hope we know and the pressure we don't know. And we'll integrate it between the two locations where we know we might be. And if we do that, well, you've certainly seen these integrals before. So the integral 1 over p is log, right? So you know that that is equal to log pressure integrated between the two limits of the lower limit of P1 and the upper limit of P2. And this term, well, G, R, and T, we could assume that those are constant is one way to do it. Let's do that, just because it makes life easy for us. We're on the same planet. G doesn't change very much as you go vertically. Gas constant certainly doesn't. Temperature could, so we're making an assumption there. And the integral of dz is just, again, z2 minus, is just z between these limits, z1 and z2. And of course, if we now substitute these limits, we get log p2 over p1. It's log p minus log p1, which is just the ratio of those. And it's equal to g RT times z2 minus z1. And that's it. And so, well, what have I not done? Well, I haven't done this right. Haven't done this. Not sure what that'll do. Will that close this thing? It may well do, so I'm not going to touch that. And so that's useful. It allows us to be able to determine these. The other thing we can also do is we can exponentiate this, just multiply exponential both sides to get rid of the log. I'm not going to have space to fit it in here, but if we do that to this side as well, then we end up with P2 over P1 is equal to the exponential of minus G Z2 minus Z1, the elevation change, over ideal gas, the gas constant for that fluid, and temperature, which is also the same as the pressure at point 2 is equal to P1 times that, right? So I'm doing every single step very laboriously, but you have it. So that's fine. So now we have a way of being able to calculate how pressure changes as we go up in elevation. If we know the two elevations that we're interested in, and we've made this assumption that temperature doesn't change as we go vertically, perhaps that's not a great assumption, but it's a good enough one for us to use. And so what we could do is we could look at how this behaves. People still writing that down, so I'll talk a little more. And so our interest is in being able to see whether it really does conform to this geometry, which if I draw it out a little more broadly, is that if you look at pressure change with elevation, then it does something like this. And this is as good a point as any to be able to make the point of our choice of pressures. This, if it's the surface of the Earth, this is atmospheric pressure, right? And we know that atmospheric pressure is 100 kPa, and we're going to run out of space. It's also equal to 14.7 psi. And the absolute pressure. Absolute pressure is equal to 0 here. And atmospheric pressure in terms of absolute pressures is equal to 100 kPa. And so we know that by the time we're in space, we're in a true vacuum, so this must asymptote to this number here. So what we've done is we've basically said at any point on this curve, we can define a couple of locations, elevations 1 and 2. It doesn't matter whether one is above the other or one is below the other. And the pressures that we'll get will be pressures 1 and pressures 2 from those. That's all we've done. And so the point is, if we know the pressure at this point here, we can calculate the pressure at this point here from this. So if we take this at sea level as an atmospheric pressure, as 100 kPa in terms of absolute pressure, then we can calculate the values elsewhere. So hopefully everyone has that down. And so we can do that calculation. And so this is just a free software. It's called Maxima. Yeah, Maxima. It's equivalent to MATLAB, but it's just downloadable. So let's do the calculation if we go up to the top of Mount Everest. P1 is atmospheric pressure, sea level, 10 to the 5 pascals. Z1 is atmospheric elevation. G is 9.8 meters a second squared. Temperature at sea level is maybe 20 degrees centigrade. Actually, it's usually taken as standard temperature and pressure is usually 15 degrees centigrade, so I guess that should be 288. It's not going to change much. Gas constant for air, 287 joules per kilogram degree centigrade. And this is just our expression. P1 times the exponential Z minus Z1 over RT. And let's see if this executes. Probably does, possibly does. And there are two expressions in this, right? Calculating, I can take this one out. Let's get rid of this. Remember that this other one's called PT, if I need to put it in. Just one curve. Sea level, so axis here is elevation. Sea level, 10,000 feet, 10 to the 5 pascals. And so by the time we go to Mount Everest, instead of being 0 pascals, which is our previous calculation, it's still 30,000. So we've lost 70%, if you like, of the pressures. If we change the elevation to be a bit more, bless you, so that Z2 is, instead of being 10,000 meters, it's 100,000 meters, then hopefully, let's see what it does. So you see that by the time you've gone up to maybe 60,000 meters, so 60 kilometers, then it's pretty thin. I mean, you're almost at the background pressure of a vacuum. Planes fly at, what, 35,000 feet, right? So 35,000, so planes fly in here. So it's actually pretty thin by the time you get there, which is why you have pressurized cabins, and if a window goes out or someone accidentally opens the door, then you're in trouble, right? Because a lot of air rushes in. But so you see that it goes down to the background of absolute zero as you go out into space.
Question.
Yes?
You used your beta 0.0075, I guess Kelvin over meter.
Which is, I use where? In this one?
Yeah, 0.0075. First, I guess.
Yeah, no, ignore beta. I don't use beta in this one yet. So we haven't done that yet.
Okay.
We haven't used beta here. I will use beta in 3 seconds. Okay? Right. So our assumption is, so you see that we're racing through these notes. So we've talked about this, this. What we've assumed in this is that the temperature remains constant with elevation. So as you get to the top of Everest or you get into the stratosphere, then you're still at 15 degrees centigrade. We know that's not true if you fly in a plane. What temperature is it at 35,000 feet roughly? Ever noticed? Minus 60-ish. 60 centigrade. Don't know what that is in Fahrenheit. 40 Fahrenheit and 40 centigrade. Negative 40 Fahrenheit and 40 centigrade, by the way, are both the same. That's one marker you might want to put away. Just interesting fact. Again, you can enliven your bar conversations with that particular little piece of information. But clearly, as you go to the top of Everest, you don't expect to be 15 degrees centigrade. And so what you can do is you can also do the same integration that we've done before, but instead of keeping this magnitude of temperature constant, you can put in what the true change in temperature is as you go up. And so this is a profile of temperature change. It's taken out of your textbook as you go up from sea level, where this is 15 degrees centigrade, to 10,000 meters, where it's about minus 60 degrees centigrade. Bless you. And so what you can do is, if you want to represent this, you'll never have to derive this, but here's what's done, is if you want to represent this temperature change, then you need to keep this in the integral, and you have to have the temperature as a function of elevation, right? And so the appropriate expression for that would look like this. The temperature at any elevation is the temperature at sea level minus the elevation times some factor. And so this factor, since this is a temperature, would have to be what? It would have to be, beta would have to be change in beta would have to be change in temperature with elevation times dz, right? This is beta in this expression. Because the units have to match up. Units of this times this have to equal units of temperature. So units of this have to be dt dz multiplied by elevation, because those two multiplied together, you get rid of this and you're left with temperature. And so you can define a parameter which gives you the temperature change with elevation. And so this elevation change, delta z, is equal to 10,000 meters. And this temperature change, dt, is equal to minus 75 meters, 75 degrees Kelvin or centigrade. Divide one by the other, and you've got your beta value, which is we just used. And so I haven't calculated this, but if you notice that the temperatures change around as you go up, which is kind of curious. I have no idea why that is, so don't ask me. But they do. So you can calculate the behavior at least to 10,000 meters by using this new expression, by substituting this into this expression, doing the integration, and you get this expression here. Slightly different. And so if you do that and go back to this, this is beta. This second expression here is that other expression. You can see, what did I have? This was comma pt, I think, right? Just this one here. And then if we run it, okay, we run it, but we should make one other change. This temperature was only good to 10,000 meters, so let's cut it back from 100,000 meters. and do it again. And you see that if you look at these cases, so the blue one is where the temperature is constant with elevation. The red one is where it changes. Well, it's not very much different, right? It changes by a few percent. So it is different, but not so much. And of course, if you wanted to do the next one above that, I'm never going to ask you to do it. You could just now use that same expression, but start the integration from 10,000 feet, where you now know what the pressure is. At 10,000 feet, you know the pressure, 10,000 meters, the pressure is equal to this. And you take 10,000 meters, you take a pressure of 2.4 times 10 to the 4 pascals as your pressure at that elevation, and then you'd use 100,000 meters, and it would calculate the pressure above that. So, yes?
Go back to your notes where the equations are.
Yep.
No, the other one.
Which other? The scribbled ones on the, okay, yep.
You have T equals TA and 3C.
Beta Z.
Where's beta?
This one. It's badly, it's missing. Sorry.
Oh.
Yeah, it's worn out. Oh, it's tired like me. It's worn off the thing. Yeah, it's beta Z.
What is it that exponents? G over
Where? Oh, yeah. Pressure location A, 1 minus beta times Z over the temperature at location A, which is what we're calling this point here. So this is going to be, if we're using 15 degrees centigrade at sea level, this is 15 degrees C. You won't have to use this expression. So I'm demonstrating the fact, so you need to know the behavior from compressible fluid isothermally. I think that's reasonable. This stuff is a curiosity, showing you how to do it, showing you that temperature has some small influence on behavior, but not very much. But hopefully that's sorted that out. Okay? Everyone okay with that? Yes? Other notes. Switch up, go up. You'll have to shout. Oh, you're right. Yeah. Okay. Thank you. Yeah. So, okay. So, fine. So, we know how to do it with incompressible fluids. We now know how to do it with compressible fluids. And I suppose that when we use this to look at manometry, which is when we use pressures to be able to measure behaviors, then we need to keep this in mind. And so the manometer rules are also given back on this, our opening shot. So we've done this. So now what we'll do is we'll use what we know, which is just a reiteration of our behaviors. We'll use these expressions to be able to do something useful in fluids. I guess we've kind of done something useful. Pressures don't change horizontally as you go from one location to the other if you're in the same fluid and can get from that point A to point B in that one fluid. If you go up, then you can subtract off the unit weight times the height. If you go down, you can subtract off you could add the unit weight times height. And if you're in a gas, the unit weight is so small typically that as you go up, you can ignore it. And the reason for that is it's a factor of 10 to the 3, 1,000 times different from a liquid, right? Density of water, 1,000 kilograms cubic meter. Density of air, 1 kilogram per cubic meter. And so we can use those rules to be able to do something useful with this information. So won't talk about that. Just talked about this. So manometry is the way in which we can measure pressures. And one way to do this is to measure the pressure in the atmosphere. So when I was growing up as a kid, we always had a barometer in the house. My parents used to tap it. Oh, it's going to be a wet day tomorrow. If the pressures were going down, right? And it's going to be a fine day if the pressure is going up, right? A high. And so one way, simple way that barometers work.
What I have here is a glass tube.
I think I
that's
turned her
about
off. Is to take a
800
tube.
millimeters long. And I've
Doesn't seem
filled
like
it
she's
with
coming through.
mercury
Don't know why.
almost to the
She's plugged
top.
in.
And I'm
Oh,
gonna
perhaps the
keep
volume's turned down.
filling it
Oh,
so
perhaps
that
you
I
should
get
listen to me
filled
instead. I can.
all the way to the
So
very
volume.
top. And then I'm going to put my finger over the end.
Basic idea is to take a tube,
Insert
fill it up with mercury,
into
put your
the
finger over the edge,
mercury.
fill it completely up with mercury with a dead end. Put your finger over the edge, immerse it in mercury, and then take your finger away.
Hold it.
The weight of the mercury will cavitate at the top of the tube. It'll turn the mercury that was there into mercury vapor. And so you have a cap of vapor at the top of the tube. Mercury belongs, oh, she's speaking to us now. And you can use that to measure pressures, as we'll see. You measure the height of the mercury. That's why we talk about 29 millimeters of mercury, is it, as being atmospheric pressure.
Millimeters.
I guess 744 millimeters as being atmospheric pressure.
What size the diameter
29 inches,
of our
I suppose,
tube
right?
is, as long as it's relatively
Can you hear that?
small.
Well, you'd rather listen to me. I can do it much better.
Let's
take it out.
Diameter.
Just disconnect it. So if you take a tube, it has a meniscus. It's a reverse meniscus for the reasons we said about surface tension, but we don't care about surface tension. You take a crickly tube, and the elevation should still rise up if you put it vertically to exactly the same limit. So how does that work? How can we measure atmospheric pressures by just measuring the height of that? Okay, great, perfect timing. So you use a mercury manometer tube, or barometer. We can use the same behaviors as before. So the idea is that we know that as we go from a location here all the way to this point here, because the pressure change with location, pressure changes with doesn't change with location as you go horizontally. We haven't changed elevation here, so there should be no pressure change. So this has to be here at atmospheric pressure. So we can, if we wish, we can use this to calculate the pressure here, which we don't know, right? Atmospheric pressure we think we know, but we'd like to know it within much finer tolerance than 101 kilopascals, 101 kilopascals, 101 kilopascals. We'd like to know if it's 101.1 or 0.2. And so what we can do is we can work from any point within here. And so the basic idea is that we could write, for instance, PB, which we want to know, is equal to this one here. And if we go up to this point here, are we adding or subtracting? We're going up, so the pressure should go down. It's PB minus unit weight of mercury times the height. And that has to be equal to PA. Uppercase A, I guess. Should have done it the other way around, of course, because it's PB that we want to know. So we could write that the other way around as PB is equal to PA plus unit weight of mercury times H. So the reason that mercury is done is for a couple of reasons. One, it's a really dense fluid, so you don't have to go up 2 stories to be able to measure what the height is. I mean, it would be 30 feet if it was water. And the other reason is it has a really low vapor pressure. And so the vapor pressure here is 2.3 times 10 to the minus 5 psi absolute. I said we wouldn't work in English units. But atmospheric pressure is 14.7. So this is 6 orders of magnitude smaller. 0. So this is basically 0. And so if this is 0, then we can measure this. We know the density of mercury. We got this. And so any small change in this elevation allows us to be able to calculate what the change in pressure is. So this is manometry. This is very simply what we do. So you write the pressure at a point, and then you move from that point all the way through your system and determine it at another point, and then you figure out the one pressure that you don't know, and you use that with all your other knowns to be able to calculate that, right? So to do that, all we will use is these sets of rules. If you go up, you subtract the unit weight times height. If you go down, you add the unit weight times height. If you go up in a gas, you add 0. And if you go horizontally in the same fluid without changing elevation, those 2 places are at the same pressure. And if it's in a closed container where the liquid originally filled this, so when it was upside down, of course, the test tube was filled all the way to the bottom. You put your thumb over the top, in a glove, of course. Mercury's not very nice stuff to handle. You immerse it in the bath, and then you drop it with your thumb. The elevation drops because it cavitates. It vaporizes in the top because of the weight of the mercury that's hanging off it, and then you're left with the vapor pressure inside. And it just happens that the vapor pressure here happens to be very low, and we can almost neglect it. If you wanted to, you could include this as not zero here and calculate that. Okay? So that's manometry. There's some examples here. Let's go through the most simple one. Yeah, this is the best example to go through. So this is a blob. So typically, say this is a pipeline with water going through it in the direction of the page, and you want to know what the pressure is in this pipeline, for instance. Very simply, what do? We write the pressure at this point. PA, we don't know. We want to find it out. And we work our way from this point all the way through this assemblage to get to a place where we do know. And this time we do know atmospheric pressure. It's of the order of 101, 10 to the 5 pascals. So we go from A. We could go up here to this point here, and we would add 5 meters plus 5 meters, sorry, we'd subtract 5 meters of 10 meters of elevation and the unit weight of the fluid. We go up, so we subtract. We go horizontally, nothing changes. We go down 12 meters now. We go 5, 5, and 2. You could also look at these all being together, right? These are 12 meters times the unit weight of water to end up at this point. Again, we can move across here in the same fluid to get to this point here. And now, to get to this elevation here, we have to go up 2 meters plus 5 meters, -7, you got it, which is this one here. So this is 2 plus 5. And then that equals whatever the pressure is here. If we know what this pressure is, if we're working gauge pressures, then the atmospheric pressure is 0 gauge, right? 0 gauge is 100 kilopascals, or 10 to the 5 pascals. And so this is 0 if we work in gauge pressures. If we work in gauge pressures, then this will also be in gauge pressures. And so now we can simplify this. We know, actually we could have gone straight to this point and just ignored this up and down, right? Would be an easier way to do it. But if we simplify this, then we know that these cancel out. We know that we're left with this 2 here, which is this one here. We know that with this is 2 plus 7, which is this here. We know the unit weight of mercury. We know the unit weight of water. And the only parameter we have is pressure. So you know the pressure in the liquid. So that's it. And if you plug and chug the numbers in there, you end up with the appropriate magnitude. So that's manometry. I mean, that's basically what you will do from this. A whole bunch of these. I mean, I can go through them. Some other examples. Does anyone have any questions, I guess, about that? I mean, it's important that you get this concept. It's really very straightforward, but they can be quite challenging. You have to figure out what you know and what you need to know. You can always write the interrelationships between these pressures just by working your way through the system, and to be able to do that. There are a bunch of examples, so I encourage you to explore those. Yeah, okay. Any questions? I'm not going to finish yet. Yes? Why are we taking atmospheric? So you can work either, we can choose to work either in gauge pressures or absolute pressures. If we work in gauge pressures are what we feel now. Right now, I feel, so gauge pressures, if you used a pressure transducer, it would say the pressure right now is 0 pressure, because the pressure behind the membrane in the transducer and outside it are the same atmospheric pressures, and so it registers this pressure as 0. If we then calculated what the pressure is in a balloon, if I blew it up, it would be relative to that gauge pressure. If we add 10 to the 5 pascals to that amount, we have the pressure in absolute pressure. So it's just the scale that we use. If we're using, the reason that we did it in absolute pressures when we did the elevation as you go up to Mount Everest is that the ideal gas law, of course, has to be written in terms of absolute temperatures and absolute pressures. And so if you remember, well, if you noticed when we did this calculation, the temperatures that we used were in terms of absolute temperatures. So because it's using the ideal gas law. So yes. Okay. We've got 5 minutes left. So what to talk about? We could also think about using manometers where instead of having it vertically, so in other words, what this is basically saying, which I didn't really say, is that so the idea here, which I didn't really say, is that you notice in this particular case, the difference in elevation between this meniscus and this meniscus is 7 meters. The pressure that is in here is roughly defined in terms of that magnitude as well. So you can, okay. So you can see that because the liquid is very dense, so this is the unit weight of mercury versus the unit weight of water. This is 10 and this is 133. So this is 13 times more dense. You could basically throw this expression away and not worry about it. Within, well, it's maybe, yeah. In this particular case, this is 7 times, this is 700 and this is 20. So it's something of the order of a few percent difference. And so the reason for using mercury is that it's so dense relative to the typical fluids we'd use, gasoline in pipelines, gas in pipelines, natural gas in pipelines, water in pipelines, is that sometimes you can just take this height and use it directly and not be too far wrong. Right? That's the reason for using mercury. The other thing is that if you want to get a really tight resolution on what the pressure difference is, instead of trying to measure very in a refined way where the meniscus is on this, what you could do is you could just canter over one of those tubes. And if you canter over one of those tubes, as in an inclined tube manometer, and you measure this length, which you could imagine would be much more sensitive, you could measure this length at better resolution than you could the height difference between these, then you can merely do the equation and write it in terms of this length rather than this height. So in other words, this delta H that you'd use here, if you write it as a length, then you can measure the length when you measure along the tube, and you have a way of getting a more sensitive reading. The flatter that tube will be, you can imagine the more sensitive the reading will be, because a small delta H will mean a big, long change in the length of the mercury in the tube. And so that's one way to be able to do it. And I'll close up with some perhaps more modern ways of measuring pressures. 2 minutes, last slide. And so you can measure pressures in a variety of different ways. You can measure it through a Boredom gauge. A Boredom gauge just has a curved tube with a closed end. The pressure changes in that tube, and because the pressure expands the tube and it has an inside and an outside radius, it canters over as you change the pressure. If it canters over and this moves up or down as you change the pressure, you can measure that displacement, and you can either have it work on a little cog on a dial, which is how dial gauges work, or you can measure it electronically with a linear voltage displacement transducer, which is LVDT. And certainly the modern way in which we measure pressures are typically either by, you could imagine a membrane and providing a pressure here. When this pressure is big enough to be able to push this membrane so you get a return flow here, the pressure that you have to apply to counter this is the pressure in the air. But by far the most usual way of doing it is by using a pressure transducer. A pressure transducer has a membrane, and that membrane deflects depending on the pressure that acts on it. It's a diaphragm. And if you measure the deflection of this membrane as a function of the pressure, you can convert that into a displacement digitally. You measure it digitally, you record it digitally, and you can calibrate it against known pressures, so you know that the voltage corresponding to this displacement is a given pressure, and so that every time you see that displacement, you know what the pressure is in the pressure transducer. And that's basically the way that pressure transducers work.